All right, so let's get this started. I'm Sergey Makarov. I'm interning this year at the Red Hat Toronto office working on system tap language enhancements. And in today's talk, we're going to start with a brief intro to system tap for people who may be unfamiliar with the technology. We're going to cover recent work done for system tap 2.0, namely support for Java collection probes, and a new purely user space backend based on Dynast. So System Tap is an open source project that's been developed since 2005 at Red Hat and IBM, intended to fill in the gaps between debugging, profiling, and tracing tools, and provide global observability in cases where none of these tools are quite a good fit to answer a question we have about the operation of a system. So what System Tap allows you to do is to write scripts that gather and observe information from all over a running Linux system. Once you write the script, System Tap compiles it into a kernel module and inserts it into the kernel from where it's able to make observations. And then you can have the script summarize what it learned and either output it to the console, log it to some kind of system log, or perhaps trigger arbitrary system commands or combine System Tap with a tool that uses this script as a backend for some kind of fancy data display. So the basic idea of writing a script to gather and aggregate information from inside the kernel is somewhat similar to dtrace on Solaris and Darwin. So a System Tap script consists of a list of probe points or with associated handler code. So the probe point represents a particular event that happens within the Linux system. And the handler code can then gather information from within the context in which the probe point occurred. So the simplest possible example in any programming language that you can write is a hello world program. So this is fairly straightforward. We have it set to trigger at the beginning when the script is loaded, and it does the obvious thing. A more involved example is a probe point that's set to trigger when function main is run in process binls, at which point we can gather and communicate information, in this case, the variable arg count from inside the function, and the actual command line arguments given to the program. So what this script will do is output a message every time the process ls starts somewhere on the system and give the command line arguments that it was started with. So in general, inside probe handler, we can have access to all kinds of useful scripting language constructs. So we can write code that loops. We can write helper functions, which can even be recursive. We can perform string manipulation or store data in arrays and perhaps compute statistical aggregates on the arrays, such as averages or running totals. There's a whole list of sample scripts available on the System Tap website giving examples of what is possible to do. To aid in gathering information, System Tap ships with a large variety of what we call tap sets, or in more common terminology, just libraries, which consists of probe points corresponding to various abstract events and helper functions that help manipulate data obtained from the context of those probe points. So in the script I showed earlier, command line string is actually a tap set function which obtains the command line arguments of the current program from any context within that program. Since the specific context this handler happens to be in is inside function main, we can write the script a little more directly and tediously by actually iterating through the argv array in that function and converting the strings in it into System Tap strings and printing those out. However, the command line string function is a lot more flexible and conceals a somewhat more tedious manipulation behind the scenes where we go into the kernel's table of running processes and obtain the command line arguments from that table. So in general, from inside the kernel, we can obtain any information in the system basically by definition. However, how tedious it is to obtain that information can tend to vary. When there's a particularly tedious manipulation, it's useful to have a tab set that abstracts it instead of having to write it each time using system tab's basic built-in facilities. So the current system tab 2.0 release ships with over 2,000 particular probe points that we can detect. These include probes that trigger on specific functions or line numbers within a program, either inside the actual kernel or inside user space programs. We have timer probes that trigger at regular intervals. We have probes that intercept system calls made to the kernel. We have probes that intercept events in various high-level subsystems, such as sending or receiving data over a network, or virtual memory events, or all kinds of things. So just to demonstrate the script I showed earlier, I have the script I showed earlier, which intercepts instances of the program bin_ls and prints the command line arguments. So I'm going to launch that script. It compiles it to a C kernel module, compiles that, and inserts it into the kernel. And now, once it's loaded, any use of the program ls is going to show up in the summary that is printing out here. So, fairly straightforward. Now, I'm going to talk about using system tab for the specific purpose of examining the behavior of user space programs. So, in this sense, system tab is an alternative to a profiling or tracing tool or a debugger. It has a lot more flexibility due to being a scripting language. We can obtain any information from the program that we need to take into account, and we can develop our own strategy for sampling it if we're doing a profiling task and for how we want to summarize it. The fact that we can access any debug info that's available for a program, so if we compile our own program, we can compile that in. And if we're examining a user space program that ships with a distribution such as Fedora, it's possible to obtain debug information for that program through the package manager. So once we have that debug info, we can use that to place probe points at specific functions or line numbers, as I mentioned earlier. We can examine the internal variables and data structures of the program by name. And from any given context, we can obtain a backtrace of the functions call sequence that led to that context. So, and in general, any information that we can access using a debugger, we can access using system tab. So the basic idea of how probing user space program works internally is basically identical to the diagram I showed earlier. We have a script that asks for information from a user space program. It's again compiled into a kernel module, inserted into the Linux kernel, which has access to the entire system by definition. And then we have tab sets that help us to extract information from the specific user space program that we happen to be interested in. And we can use that as the basis for whatever summary we want to compile for that. One advantage of this is that we can perform online instrumentation. Namely, if we have an already running program, the tool does not require us to either shut down the program or to suspend its operation to examine it. So in general, it's a non-disruptive approach to examining its behavior. This compares favorably to something like a debugger where the running of the program is suspended while you examine the contents and decide what command to give it next, or next to certain profiling tools which have to be launched together with the program in order to be able to examine it. So to demonstrate how examining a user space program can work, I have here an extremely simple program I've written in C++, which just has a state variable that it increments every 4 seconds. So I can compile that with debug info included. With debug info included. And launch a copy of that. So pretend that this isn't laughably simple. Pretend that this is some kind of production server program. And it's running, and there's something we want to learn about it that is not obvious from its actual behavior. So in this case, I have a system tap script that simply intercepts every instance of when the function ping is called and prints out the process ID of the process that we've intercepted, whose ping call we've intercepted, and the value of the state variable. So if I launch this system tap script without shutting down the program in the other window, it is going to attach to that program and detect all calls to the function ping that occur in it. And we can observe what's happening without having to take this down and relaunch it with a debugger or profiler. Another interesting thing that we can do is to, yes?
So here you know the name of the function. Is it possible if you wanted to know what function, like without knowing the name of the function?
We do have wildcards.
Generally, we can either obtain the debug info that comes with a program and use that, or if we have no information about the program, it may be possible to try and probe it by a specific address inside the object code. So system tap can be set to trigger on a specific address inside the code as well. In general, that's available as well. So I think we have a facility called StapL, and we put in a wildcard probe point here. Let me see if this works. But the basic process is something like this. I can put in a wildcard probe point here, and it should give me a list of the specific probe points that happen to match that function. Yeah.
So you'd have to surround that by like a probe point.
All right.
It is possible, yeah. You need to use wildcarding. What you do is you would essentially set for that process, say for each function, and then do the tap sense that Surya mentioned earlier. You can simply say print out the probe function, and it'll list out all the functions that it hits, and it'll give you the name and any variables that's passed to it.
Just a double quote, that's RDF.
Okay. I'm not sure if actually attaching to all of the functions using a wildcard requires you to have debug info still. So anyhow.
Does it have escape characters or not?
Sorry, what was the question?
Do you require escape
Yeah, no, if it's a special character that you don't want to use, that's not a character of the or feature of the language, then yeah, you want to skip it.
Oh, sorry. Let me just try this and I'll continue with what I was doing earlier if it doesn't work. Maybe I should have coded that. Okay, so it actually lists the specific functions inside process a.out that we can attach to. So we have a bunch of, I think, C runtime shims, and we have main and ping. So it is possible to examine which functions in the file we can attach to. All right, so to continue with the demo, I can attach to multiple instances of the same program and aggregate the information from those as follows. So let me continue running this one in the background and launch another instance. Then relaunch the script. So it will show us the information from both of these programs and their current state. So we can combine information from several instances of the same program. We can combine information from instances of different programs. We can combine information if we wanted to from a user program and information we obtained from some kernel subsystem. So in general, this is a good starting point for trying to write a script that tries to integrate information from several components of the system to answer some question that we have about what's going on. So, sorry, let me just shut these down. So that's user space program probing. So in general, in case you missed it, what's the value of having system tap around? It's a scripting language for gathering information about what's going on in your system. Compared to what it's doing underneath, namely writing a kernel module that gathers that information, this is much safer and simpler to accomplish using system tap. Not only do you have the actual language which performs safety checks and has resource limits that keep you from doing something that would crash the kernel, it also has a massively useful repository of glue code in the form of the tap sets to aid you in actually interacting with various subsystems and extracting information from them. Relative to more specialized tools, it's useful if there's a question you have that the other tools that are available don't quite answer for you. So if you have something unexpected, you can start using system tap. It may take longer to put together the specific aggregate of information that you're interested in relative to a tool that just has that aggregate built in. But you can answer unforeseen questions. Another point that's slightly outside the scope of this presentation, but that it might be interesting to highlight, is that it's actually fairly easy to extend the tap sets themselves. Those are written using the system tap scripting language itself, plus snippets of embedded C code which runs within the kernel. So if you can imagine gathering information using C code from the kernel, it's a fairly straightforward process to wrap that into a tap set and make that available to a system tap user in a safe and secure fashion. Now, I covered using system tap to examine your own user space programs. So there's several directions that we want to improve this functionality in. First of all, we have support for a variety of languages. C, I showed you probing a script a program that happened to be written in C++. There's even support for various scripting languages, but we always want to improve our ability to examine these languages. In particular, when there's language concepts that don't correspond to the ones in the C runtime, we need to write a particular support for them into the tap sets. For instance, if there's a garbage collected language, we want to have probe points that let us examine the behavior of the actual garbage collection, since that may be relevant to examining and understanding the performance of our programs. Another point is that the whole scheme of having SystemTap compile a kernel module and inject it into the kernel just because you want to study your own user space program is a bit of a roundabout way to do it. It raises the question, if you're just a user and you want to study your own program, you either need to run SystemTap under administrator privileges, or we need to have a whole special security scheme that makes sure you can only use SystemTap to obtain information that you're allowed to see in the first place. In general, there's a whole procedure to do this. Namely, there's a special group called STAP user has to be set up on the system. The users that need to use SystemTap in an unprivileged mode need to be added to that group. Then the administrator needs to set up a compile server outside somewhere that the unprivileged users can't access it except to send it scripts to compile, since otherwise they'd be just using SystemTap under their own user and they could try to tamper with the safety checks that are built into the language. And once you have that compile server and it certifies and compiles scripts that you submit to it, then you can examine your user space program. But it's not ideal. In general, administrators aren't going to enable a piece of software that compiles and injects kernel modules into your kernel lightly, no matter how many safety checks you add to the tool. So we want to have some kind of mechanism that injects modules perhaps into the actual program that you're observing, so the administrator does not have to worry about what you're doing. So for the rest of the presentation, Lucas Burke is going to cover recent work that's been done in these areas for SystemTap 2.0. Okay, and now we have to fiddle with the mic. So, see better than. Your pocket somewhere.
Cool. Thanks, Sergey. Everybody, my name is Lucas. I was a former intern on SystemTap and I've returned full-time at Red Hat. So we're going to start with Java. So it's generally accepted as one of the most widely used programming languages in the world. And just as a frame of reference for the remainder of the talk, and in case you've been sleeping since 1995, a couple features of it is object-oriented. It's considered write once, run anywhere using the Java virtual machine. And it's got automated garbage collection, which this is the point we want to highlight. So in order to use automated garbage collection, there's a series of algorithms that has been developed over the years. They vary depending on the purpose and the situation you want to use them. And a couple examples are the serial collector, the parallel collector, the parallel compacting collector, the parallel young generation collector, the concurrent mark sweep collector, and the latest and greatest, the garbage first garbage collector. Now, if you're sitting in these going, oh, whoa, I didn't know all these existed, what's going on here? You're not alone. There's extensive documentation showing when you should use each and the proper use case. But ensuring that and observing the operation and behavior is the big question we're trying to make sure, and what the driving goal behind these extra probe points were. So there are existing tools to monitor Java virtual machines, don't get me wrong. They include Thermostat, which is open source, JRocket Mission Control, Visual VM, and there are also command line options that the JVM, you can pass to the JVM and it'll specify and output information. And these are all fantastic tools, don't get me wrong. We're just interested in a slightly wider scope, and we also want to make sure that you don't have to shut down the JVM to print out that information. The command line options have to actually shut it down and restart, passing those parameters in. So we would like to come at this from a SystemTap perspective. So what we've done is we've added a whole bunch of new probe points in the garbage collection subsystem, and I'm going to just show them to you. SystemTap, as we showed you before, has the functionality of listing specific probe points. And we're just going to show you the hotspot related ones in relative to the garbage collection. So this is slightly lower resolution than I like, but that would be, so you'll see a whole bunch of these going down. It's hotspot specific, and for this example, it's a collection of parallel scavenge, and this is the beginning point. Each probe point will have a name, an address string to go with it, so where this collection is happening, and a cause. So there are various reasons why garbage collection occurs, and we want to know why. That could be really helpful. As well, we have an aggregate called probe str, which essentially will print out all the information in a nice, easy to read format whenever a probe point's hit. So it just makes writing a script a bit easier. We have probe points for the various algorithms that I mentioned earlier, and also actual moving of generations and memory blocks in the Java virtual machine. So let's see these probe points in action. To do that, we're going to use a benchmarking software called Decapo. Now, it's a Java benchmarking suite, and its primary feature is the fact it uses real-world applications to give you meaningful results. So one of its benchmarking suites is, it runs a set of Eclipse functionality, and that should give you, a more accurate representation of what the Java virtual machine is doing. So let's step through the script that we're going to use. We start off by invoking system tap, and we're going to say so the probe point will be any hotspot garbage collection begin. Okay, so whenever something starts, we want to know. And what do we want to know? The handler will be just a printf function where we say, okay, we're beginning, and we want to print out all the relative information to that garbage collection beginning. Likewise, we want to see specifically where every garbage collection ends and all the related information to that. So just a simple beginning and end. You could extend this to say, include the time spent in garbage collection. That part's up to you. System tap will actually invoke the benchmarking Decapo suite, and we're going to run the Eclipse benchmark. And just so it's easier for us to read the output of system tap, I'm going to make all the Decapo output to a file. I should cap this. So just like I showed before, this is the script. I've specified where the Java virtual machine is to mine, and let's just run it. So it's inserted the kernel module, and the Decapo is starting. It's in the background gearing up. And you can see the beginning and end, and you can see here there's scavenges. So those are miniature collections. You're going to see the address in which it occurs on my machine, and then the cause. So this is a tenure generation was full, so we've decided to start the garbage collection. And that'll go. You'll see different collections occurring. See, we've got a G1 evacuation pause. And you can profile your application on the JVM without having to shut it down. So if you've programmed in general, you may know that it's not just Java that runs the hotspot JVM. There are other languages as well. You have Ruby or JRuby and Jython are two big ones. So one of those benefits is the fact that you can write JRuby or Jython and still have these probe points hit. So as an example, I have a JRuby script. JRuby has a library that is a benchmarking tool. And just as a simple rundown to this script, we're going to benchmark essentially just one operation being repeatedly run 1,000,000 times. So I won't run it all out for you, but that's just the basics. So the script again. It compiles it, inserts it. As you notice, we cache it if we've run it before, so you have faster startup time. And despite the fact that this is a JRuby script, we're still hitting the hotspot probe points. So it's got a wider application. Cool. Did we have any quick questions on that? No? Cool. So we're going to switch gears a little bit now to something Sergey alluded to earlier. Consider where you're administrating a number of developers, or perhaps a bunch of students in a lab. Or you don't have administrator privileges on your own machine, but you still want to safely probe your own processes, right? That shouldn't be a hard thing to do. But how do you safely use system tap in those scenarios where you're inserting a kernel module, which is a privileged process? So we came across this issue, and our solution was provide a user space only backend. And to do that, we found a tool called Dynast. So as a bit of background for Dynast, It's a project that was started by the University of Maryland and University of Madison, Wisconsin, or Wisconsin-Madison, excuse me. And it's licensed under the LGPL, which means we can use it and we can benefit from it. And essentially, it's an API which utilizes ptrace and inserts code into a running program, and we can change the code that's running based on our needs with the SystemTap script. This essentially has two big benefits that, as a SystemTap developer, and that we wanted. Mainly is high performance, fast. We don't want to interfere with the program running. And it's architecture independent, so we don't have to worry about that aspect of it. So just as a refresher, and to reiterate the fact, this is a typical SystemTap process. We have the script, we generate the kernel source, and we compile the kernel module. And all as the same as before, I mean, you just have normal user privileges to do that. It's the actual running and loading that kernel module that's the escalated privileges that we're trying to avoid that. So as a comparison, Dynast, most of it's the exact same. You still have a SystemTap script, foo.stp. We're still going to generate user source from a C file. But instead of a kernel module, we're going to compile a user module or a shared object library, for a term of it. And loading a shared object library is not an escalated privilege task. We remain in a ring 3, and programs do it all the time. So what does this mean for you? Well, it's a real simple invocation. If you've used SystemTap before, I mean, it's just you append runtime equals Dynast. Not much difference in terms of language. There's no need to join STAP dev or STAP user groups. So, I mean, there's no, you don't need to mess around with the user groups or set up a compile server, certify the compile server. And then we remain in ring 3, like I said before. There's nothing that we need that we don't have. And we should note there is a slightly modified set of probes available to us. We still have process foo, timer, start, and we do still have guru mode, which is embedding the C into our scripts. We still have access to that. We can still do that. There's just a pretty powerful functionality. And by the nature of the beast, we'd no longer have kernel or perf probes, but if we're going to remain in user space, we wouldn't have any knowledge of that anyways. So I'm going to run through a couple demos for you. Clear this off. Let's say I got 2 users on my system. Alice, whose password is definitely not the same that you have in your luggage, and Bob. He's got a totally different password, I swear. So just going to ID. Alice has no escalated privileges. She's not part of any unique group. She's just a regular old user. So let's see. For the first one, like we said, we got SystemTap. We've appended runtime equals Dynast. And all we want to do here is, for every function that we hit, we want to log the probe point and the information regarding that. And Alice has had a simple program that's got a whole bunch of functions in it. So let's run that. Notice how we're actually using an SO versus a KO here. And then for each function in our program, we print out the probe point. And hey, that's us. So that's all well and fun. But let's take the same program we had before, the C++, where it's a simple C program. It sleeps. We want to get out the state every 4 seconds. So let's run that. Once again, using the runtime equals Dynast. And we got this evil user Bob here. Goes, oh, I want to probe her processes. So he's pointing the process at Alice's a.out, and he wants to do the exact same thing for every function ping. He wants to print stuff out. But he can't do it. We're not going to let him. We just give him a syntax error and say, we don't have a match for that process. So it's still safe despite the fact that you're using SystemTap, which is a pretty powerful tool. So, I mean, this just adds an incredible amount of convenience to being able to use SystemTap. And that's it for Dynast. Did you have any questions on it?
I have a few questions. So
Sure.
The first question is, can you get information on a runway process? So let's say, I mean, if it's 100% of your CPU and you cannot do anything, that's one situation. But let's say if you have a process that's hogging up a lot of your CPU and you want to find out information. Let's say you've compiled all the
Debug info?
symbols.
Yeah.
So how would you go about doing that? Is it possible to do it with system?
Yeah, for sure.
The other question that I had is, can you do a comparison between, I'm not familiar with dtrace, but I just want to know logically, like, how different is it from dtrace?
I mean, it's the same idea. The same, we want to be able to probe the scope. I'm not terribly familiar with dtrace.
In general, just on a superficial level, dtrace is implemented internally differently. Instead of compiling a dtrace script to C code and then compiling that to a kernel module, dtrace has a VM inside the kernel that's loaded in advance, and a dtrace script is compiled into bytecode for that VM. So for systemtab being compiled into C, that means first of all that the scripting language is somewhat more flexible. It means that when we're actually developing systemtab, there's a whole set of procedures to go about to make sure that the script code is adequately safety checked before it's compiled into C, so the resulting C doesn't hog too many resources at a critical point in the kernel or doesn't break something. And another thing is that it's easier to actually add tab sets to systemtab because you're writing them as systemtab scripts with a bit of C in them. So.
On our website, she'll show at the end, on our wiki, there's a comparison of the two tools.
And to answer your first question, I mean, we do have tabset and functionality. So all you would do is, instead of a.out, whatever process is hogging the machine, you would point it at that process, and you can change whatever functionality on this side you actually want to look at. We do have in our examples, which I'll point to at the end, we do have a similar scripts as function or top, so you can look at which programs are taking up more memory or CPU time.
Yeah.
And they're the perf probes as well.
You could try things like having a timer probe that fires at regular intervals and just samples which process we're currently in. So that's probably a good way to start getting a sort of top type idea of which process it's spending time in.
Does that answer your question? Yeah. Okay. And you guys?
Some such scripts that do that, they make samples vector, etc.
Yeah.
And just so you guys know, all this functionality is actually in systemtab 2.0, which is in the latest release of Fedora 17 right now. And all the Java aspects of it are in ICE-T right now. So if you get the latest clone from the forest, you'll have it.
Is Saad part of this
Pardon me?
program? You heard some fellow named Saad? Is it?
Oh, Saudi, he works for Reddit, yeah.
Okay, is he? He told me he wrote like a little module with you, but not sure so with your group or not.
Sorry, I didn't catch that.
Did he I'm not sure he's involved in this part of the process or project you guys are working on.
I think he works on a different one. I'm not sure. Cool. All right, so this is how you find us. We got sourceware.org/systemtap. We have a mailing list, and if you're on IRC at all, pound systemtap on freenode.net. So thanks for coming out, guys.
Yeah. So just one last thing. On the systemtap website, again, just to emphasize, a good starting point to look at is the examples page, which just gives an idea of what's the possibilities based on the building blocks that we showed in the presentation. So in general, it has examples that duplicate many sort of profiling or tracing tools on a very simple level, just to show how you'd go about various strategies that you'd try to gather information.